thermodynamics. So in the previous lecture, we had seen how a numerical problem can be solved regarding the concepts of second law of thermodynamics. And in the previous lectures, we have seen the basic concepts of and the basic statements of second law of thermodynamics. We have carried out the discussions on Carnot cycle and many other things. The absolute thermodynamic scale of temperature did provide us a very important information about the relationship between the heat transfer and the temperature at which these heat transfers are taking place. So in the end of the last lecture, we had solved a numerical problem. So today we'll carry out some numerical problems. I hope that during the solution of these problems, it will help you a lot. So let us start the first problem. So as you can see, a domestic food freezer maintains a temperatures of minus 15 degrees Celsius. The ambient temperature is 30 degrees Celsius. If heat leaks into the freezer at the continuous rate of 1.75 kilojoule per second, what is the least power necessary to pump this heat out continuously? So let us draw a diagram by which we can explain this condition. Okay, so let us draw it. So this is the source which is maintained at T1. Now T1, so we'll see what do you mean by this T1, and this is your refrigerator. So this refrigerator needs some power or external work so that it can perform according to our requirement. So let us assume this is W, and this refrigerator is continuously pumping out this Q2 heat. Okay, and this is the heat which this refrigerator transfers to the source. Now you can identify this is the space which needs to be refrigerated. So this domestic food freezer should maintain a temperature of minus 15 degree Celsius. Okay, so this T2 becomes 258 Kelvin, and the ambient temperature is it will be 303 Kelvin. Okay, so now what happens? Heat leaks from the ambient to the freezer. Okay, so this freezer needs to pump this heat out. Okay, so the refrigerator needs to maintain a certain temperature, and from the environment or the ambient, heat is coming out. So the refrigerator needs to pump this specific amount of heat or specific rate of heat continuously to the outside. So it is quite observable that this Q2 is nothing but this 1.75 kilojoule per second. Okay, now the question is, what is the least power necessary? Now whenever you are talking about the least power requirement for a refrigerator, it means it is it is trying to indicate a reversible case. In case of heat engines, reversible heat engines provide you the maximum efficiency. That means it provides you the maximum work output. Whereas in cases of reversible heat pumps or reversible refrigerators, you need, uh, if it is mentioned as reversible, then the work input which is necessary, it becomes minimum. Okay, so this is the diversity of the reversible heat pumps and reversible heat engines. Actually they are um, completely opposite to each other. So you must understand the fact heat engine gives you the maximum output, and refrigerator or heat pump, reversible refrigerator or reversible heat pump, requires the minimum output for the reversible condition. Okay, so now if it is a reversible refrigerator, then it is simply, you can write Q1 by Q2 is T1 by T2. Now the question is, what is the least power necessary? That means what is the work done per unit time? What is the work input required per unit time, so that this refrigerator can pump this certain amount of heat continuously. So now this is for the minimum power requirement condition or the least power requirement condition. It indicates a reversible case, and you know that Q2, you know it, T1 you know, T2 you know, so you can simply take this Q1. Okay, by putting the values, it will be 303 divided by 258 into 1.75. Okay, so this is the case, and after doing the relevant calculations, it will give you 1.65. Okay, okay, so I'm sorry, it will give you 2.06. It will give you 2.06. Sorry, I will do it in a much better handwriting. It will be 2.06. Okay, so now the question comes to calculate the least power necessary. So you can do it by this way, by the conservation of energy principle. It is very simply understood that Q1 will be equal to W plus Q2. So W will be Q1 minus Q2. Okay, so W is equal to Q1 minus Q2. That means 2.06 minus 1.75. That gives ultimately 0.31 kilojoule per second. Okay, so the trick in this problem was this word. What is the least power necessary? So you must understand it is referring to a reversible case. Okay, so whenever you are dealing with a limiting case, that means the maximum power uh, output for a reversible heat engine, then it will be a heat engine case. Okay, so let us move on to the next problem now. Okay, so here you can see that a heat engine is used to drive a heat pump. The heat transfers from the heat engine and from the heat pump are used to heat the water circulating through the radiators of a building. The efficiency of the heat engine is 27% and the COP of the heat pump is 4. Evaluate the ratio of the heat transfer to the circulating water to the heat transfer to the heat engine. Okay, so let us construct the diagram which will help you to understand the problem. Then we can move on with the calculations. The calculations is not not complex, but the main thing is regarding to construct a diagram and to understand the problem. Okay, so now I have just drawn the diagrams so that it can be understood in a much better way. So as per the problem, you can see this heat engine is used to drive the heat pump. That means the work which is being produced by the heat engine, that is completely utilized to drive the heat pump. That means the work input of the heat pump equals to the work output of the heat engine. Okay, now the question is, this efficiency of the heat engine has been mentioned as 27%. This efficiency is mentioned as 27%, and the COP of the heat pump is mentioned as COP of the heat pump has been mentioned as the 4. Now here we can see the heat rejection of the heat engine and the heat uh, um, rejection of the heat pump. They are taking place in the same temperature because they are together used to heat the water circulating through the radiators of a building. So this information is very important to us, and it is well understood that the heat at which this heat rejection takes place and the heat rejection takes place for the heat pump, they are same. The temperature remains same. So what we have done actually, we have connected these two equal temperature cases, and we have just changed the direction here. Okay, that means uh, logically it is absolutely correct, but we haven't kept two different thermal energy reservoirs. We have made it a single one so that we can understand the problem in a much better way. So this diagram has evolved from here. Okay, from the understanding of this diagram has made us to create this diagram, which will help to solve the problem. So now this diagram is not required. Okay, so the next one, the right one, that means this diagram is enough to solve the problem. Now the question is, evaluate the ratio of the heat transfer to the circulating water. So this is the circulating water. Now what is the heat transfer here? Q2 plus Q4. So you need to calculate Q2 plus Q4. Okay, ratio of the heat transfer to the circulating water to the heat transfer to the heat engine. Now what is the heat transfer to the heat engine? This one. From the source, this is Q1, heat is being transferred to the heat engine, so divided by Q1. So the question is to find out the ratios between Q2 plus Q4 divided by Q1. That is the question here, right? So now how we can solve this problem, that is our objective. So we know this efficiency can be written in the terms of uh, like this. We can write this term 1 minus q1 by q2 can be written as 27 by 100. Again, we can write q1 by w as 27 by 100. Okay, so solving these two equations, if we solve these two equations, we'll get q2 in terms of q1, or I think this is not required at all. So from this equation, it is well known that q1 by q2 would be, I'm very sorry that I have written a wrong formula here, it will be q2 minus q1, because I am once again repeating the formula, because it is always heat rejected by heat taken. So q2 by q1, q2 by q1 becomes 73 by 100, and Q2 can be written as 0.73 Q1, right? So this Q2 can be written as 0.73. So let us write it here because it will be required to us. Okay, so let us clear this up. And now coming on to this information here, we can write this Q4 is the desired output. Okay, when W is your heat input. So Q4 by 4 you can write as Q4 by W you can write as 4 because this is your COP. If you remember the formula, COP always refers to the desired output divided by the work input. So Q4 by W can be written as 4. Now Q1 by W was equal to 0.27. Okay, so W, oh, again, very sorry, W by Q1 was equal to 0.27. Okay, so here we can write, you can write Q4 divided by 0.27 Q1 is equal to 4. That means what we are trying to do? We are trying to express this term and this term in terms of Q1 so that the ratio can be calculated very easily. Okay, now this Q4 becomes 1.08 Q1. Okay, so Q4 becomes 1.08 Q1. This is very simple. Now if you add it up, if you add up Q2 and Q4, you will get 1.81 Q1, right? 1.81 Q1 you will get divided by Q1. So the ultimate answer is 1.81. So the ratio becomes 1.81. So this is how we can solve this problem. So whenever you need to understand the problem so that you can do this step. This step is the most important one. After you have understood this step and you have drawn this diagram, then the problem becomes very easy. It is just some numerical solving, nothing else. Okay, so with this understanding, let us move on to the next one. See what is in store for us. Okay, so here you can see a heat engine operates between the maximum and minimum temperatures of 671 degrees Celsius and 60 degrees Celsius respectively, with an efficiency of 50% of the appropriate Carnot efficiency. It drives a heat pump which uses river water at 4.4 degrees Celsius to heat a block of flats in which the temperature is to be maintained at 21.1 degrees Celsius. Okay, so it drives a heat pump which uses river water at 4.4 degrees Celsius to heat a block of flats in which the temperature is to be maintained at 21.1 degrees Celsius. Assuming that a temperature difference of 11.1 degrees Celsius exists between the working fluid and the river water on the one hand and the required room temperature on the other. Okay, and assuming the heat pump to operate on the reversed Carnot cycle but with a COP of 50% of the ideal COP, find the heat input to the engine per unit heat output from the heat pump. Okay, so you can find the diagram have been drawn now, and now the question comes how I have drawn this diagram. Okay, so I have something left here. It is Q3. Okay, this is okay. Just let me rewrite it so that it can be clearly visible. So it is Q3, and the heat taken by the heat pump will be Q4. Okay, so now what happens here? There is a heat engine which is working between these temperature limits, and it is driving a heat pump. Let us not complicate the problem now. Now what happens in this heat pump? It is what is the heat pump doing here? It is heating up the river water. Okay, so the river water is at 4.4 degrees Celsius, and then it heats up. The heat pump heats up this river water and sends this river water to the flags at a certain temperature of 21.1 degrees Celsius. So here this one and this one is the temperature of the river, and here the working fluid temperature is mentioned. Okay, now it is uh, it is to be understood that the COP of the heat pump would depend on the temperatures of the working fluid. So the constituent which the heat pump is heating up doesn't affect the performance of the heat pump. It is a working fluid which influences the efficiency of the performance of any heat engine or any heat pump. Okay, now here a specific condition has been mentioned. Assuming that a temperature difference of 11.1 degrees Celsius exists between the working fluid and the river water. Okay, so this is a very important condition. Now what I will do, I will rewrite the temperatures here. So this temperature is easily identifiable. It is 67.1 degrees Celsius, 671 degrees Celsius. Okay, so in Kelvin it will be 944 Kelvin. Okay, so it will be 944 Kelvin. Okay, and this one, this T2 would be 333 Kelvin. Okay, simple, because the heat engine works between the maximum and minimum temperatures of 671 degrees Celsius and 60 degrees Celsius with an efficiency of 50% of the appropriate Carnot efficiency. So let us find out the Carnot efficiency. Okay, so it would have been 1 minus T2 by T1. You know that. So it would be calculated as 3 3 3 divided by 944, right? So you will get a value of 0.647. So this is the Carnot efficiency. Now the original efficiency of the heat engine, now we can write eta heat engine. Okay, so this will be the original one, right? So this will be the original efficiency of the heat engine. So just give me some time, I'll write in a clear way. So it will be heat engine. The efficiency of heat engine would become 0.3235. Okay, so the efficiency would become 3235. Okay, now we have found out the efficiency of the heat engine, right? So I can clear this up. Okay, now what happens here? It drives a heat pump which uses river water at 4.4 degrees Celsius to heat a block of flats in which the temperature is to be maintained at 21.1 degrees Celsius. Then this T3 would be this 21.1 degrees Celsius, right? So the temperature would become 29.4.1 Kelvin. Simple as that. Just very simple. Just a basic addition here, and it is 4.4 degrees Celsius. So 277.4 Kelvin, right? Okay, now assuming that a temperature difference between 11.1 degrees Celsius exists between the working fluid and the river water. So here you will find, here we will write the temperatures of the working fluid. Okay, so let us consider TF3. This is the temperature of the working fluid. So here you need to maintain a temperature difference of 11.1 degrees Celsius. Then what will happen? You just need to add it up so that a temperature difference of 11.1 degrees Celsius would be maintained here, but here you need to subtract it. Okay, now why is it so? Because the heat pump is heating up, so since the temperatures at which the heat pump is serving the water, okay, this is mentioned, this these temperatures needs to be maintained at the specified rates. Now working fluid, uh, when when it is receiving heat, the working fluid will not be so much heated. Okay, but so the working fluid, the objective of the working fluid is that when it is taking heat, it will be at a low temperature, but when it is delivering heat, which is our requirement, it should be at a very higher temperature so that heat can be extracted from it, which is our desire, which is our specific requirement. So here, um, this TF4, that means the temperature of the working fluid, upon which the efficiency of this heat pump, I'm sorry, the COP of the heat pump depends. So it would be found as 266.3 Kelvin. How can we find it? We are just subtracting this 11.1 from this one. Okay, now the question is, you need to uh, find the COP of this heat pump for the ideal condition as well as for the actual condition. Now it is mentioned that the COP, the ideal COP, is uh, twice of the actual COP, right? So first you need to find out the ideal COP. So first, initially you need to find out ideal COP. Okay, so it is very simple. So I have told you the COP would depend on the temperatures of the working fluid, not the river water. Okay, so ideal COP can be calculated. TF3, we can write TF3 divided by TF3 minus TF4. Now you know this TF3 as 305.2, and you know this TF4 as 266.3. So you will find the COP becomes 7.86. Okay, so the COP becomes 7.86. Okay, so now the actual COP. So here I would write the actual COP. So it is half of the ideal COP. So it is very simple. It will be 3. It would be 3.93. Okay, so it would be 3.93. Very simple. So now we have found out the, So now we have found out the ideal COP. Now the question comes is that the question is find the heat input to the engine per unit heat output from the heat pump. That means if this Q3, if Q3 is equal to 1 1 kilojoule, then find the heat input to the engine. That means you need to find out Q1. So this is our question. If Q3 is 1, then what would be the value of Q1? Okay, this is our question. So what I will do, I will just clear it up because it will be not required now. I will also clear the drawing because it would be also not required. So I'm just clearing all the diagram here, making some space over here. Now we can move on to the problem. The question is, if Q3 is 1, then what is the value of your what is the value of Q1? Now COP, if you remember the diagram, then the COP would have been Q3 divided by W, right? It is very simple. So now this W would be Q3 by COP. That means 1 divided by 3.93. So it would be 1 divided by 3.93. Okay, so since it is 1 divided by 3.93, we can calculate the value of W, and you will find it becomes 0.2549 kilojoule. Okay, so W becomes 0. It becomes 2549 kilojoule. Okay, so it becomes 0.2549 kilojoule. Okay, now we know this efficiency, right? So I'm just clearing it. We know this efficiency. Now it is very simple. W by Q1 is your efficiency. So you have found out the value of W. You know the efficiency, which is 0.3235. 0.3235. Now you need to find this Q2. That would be W divided by 0.3235. Okay, so this is very simple, and you will find the value of Q1. So I need to calculate it, so just give me some time and I will calculate. I'll give you the final result. So after the calculation, this is the value which we obtain. So now, so this is our answer. That means per unit heat output from the heat pump, the heat input would be 0.787 kilojoule per kilojoule. So this refers to the per unit heat output, and this is your heat input to the engine. Okay, so this is per unit heat output, that is 1 kilojoule. So per 1 kilojoule of heat output from the heat pump, you will receive 0.787 kilojoule heat input. Okay, so I think we have completed the problem, and now we would move on to the next one. So next one, let us see what is the problem written over there. Okay, so here we can see a reversible engine operates between temperatures T1 and T. The energy rejected from this engine is received by a second reversible engine at the same temperature T. The second engine rejects energy at temperature T2. Okay, show that temperature T is the arithmetic mean of temperatures T1 and T2 if the engines produce the same amount of work output. Temperature T is the geometric mean of temperatures T1 and T2 if the engines have the same cycle efficiency. So this is a very useful information which will help you to solve many problems. Okay, so let us try to solve this problem. Now, uh, so let us just give me some time. I will draw it. So now here you can see the diagram. The energy a reversible engine operates between temperatures T1 and T. So this is the first reversible engine, engine A, which is operating between the temperatures T1 and T. The energy rejected from this engine is received by a second reversible engine at the same temperature T. So here you can see the energy rejected by the here you can write this Q3 is equal to Q2 because the energy rejected by the heat engine A is received by the heat engine B. Okay, so you can write Q3 equal to Q2, and this heat engine B, it rejects the heat at temperature T2. Now let us try to solve the problem here. Temperature T is the arithmetic mean of the temperatures T1 and T2 if the engine produces the same amount of work output. Okay, so now the question is WA is equal to WB, right? So you can write Q1 minus Q2 is equal to Q2 minus Q3. Okay, now you know that Q1 by Q2 can be written as T1 by T, whereas you can write Q2 by Q3 as T by T2. So this formula can be written because it is mentioned that the engines are reversible. So you know, for reversible engine, according to the principle of absolute thermodynamic scale of temperature, the ratios of the heat transfers will be equal to the ratio of the temperatures. Okay, now if we divide this equation by Q1 and we divide this equation by Q1, let us see what happens. So when we divide this equation by Q1, it means 1 minus Q2 by Q1. When I am dividing this equation by Q1, it will give us this value Q2 by Q1. Okay, let me just check if this is the right way or not. Okay, so it will be Q3 by Q1. Okay, here this Q2 by Q1 can be written in the temperature format as T by T1, and this Q2 by Q1 can be again written as T by T1. Now comes the question to find out the value of Q3 by Q1. Okay, so what we can do here is that we can write Q3 divided by Q2 into Q2 divided by Q1. Okay, so we are expressing this Q3 by Q1 as the multiplications of Q3 by Q2 into Q2 by Q1, and you know Q3 by Q2 Q3 by Q2 would be T2 by T. So I can replace it here. I will write here T2 by T, right? T2 by T. And Q2 by Q1 would be T by T1. That is as simple as it is. So it would be T by T1. Now what is the result? Ultimately these two T are alike terms, so they will be removed from the equation, and ultimately this equation will remain valid. Okay, so this is simple mathematics, and ultimately you will get 1, so 1 plus T2 by T1, which is equal to 2T divided by T1. Okay, I think you have got it. Okay, now what happens here? T1 plus T2 divided by T1 gives you 2T by T1. Now I will just clear up this space. So here the problem is almost completed. So here you can see that T becomes T1 plus T2 divided by 2. Very simple. So T becomes T1 plus T2 by 2. So you can easily prove that this T is nothing but the arithmetic mean of the temperatures T1 and T2. So when the two engines are producing the same amount of work, it can be proved that the temperature T, or the intermediate temperature, can be written as the arithmetic mean of the temperatures T1 and T2. Now comes the second part, where it is mentioned that these two engines will have the same efficiency, same cycle efficiency. That means eta A is equal to eta B. So this is very simple. In terms of temperature, how you can write this efficiency? It would be 1 minus T by T1 for reversible heat engine A, and for reversible heat engine B it would be 1 minus T by T2. So you can get T by T1 is equal to oh, I am very sorry, it would be the minimum temperature divided by maximum temperature. For the case of heat engine B, it would be T2 by T. Okay, so just please check it. So it would be T by T1 is equal to 1. Oh, sorry, there is no need of 1 because I am just clearing it all. So here you can see T square becomes T1 into T2, right? Or T2 is T. Okay. Please again check this. It will be T square, not T suffix. So this T would be written as the geometric mean of T1 and T2. So when the two engines have same efficiencies, then it is easily proved that the temperature T would be geometric mean of the temperatures T1 and T2. Okay, so I hope that you have understood the problem. It is a very simple problem, I believe, the most simple problem of this series. So now let us see these assignment problems. So these assignment problems you need to solve. If you are able to solve all these problems, then I think there will be no problem regarding the conception of of your uh, of your concepts in the second law of thermodynamics. So with this I will be ending my lecture today, and in the next lecture we'll start discussing a very important and very interesting topic which we call as entropy. So hope for the best and see you soon in the next lecture. So for that, till now, uh, the lecture ends here, and for the next lecture, um, goodbye. Till the next lecture, goodbye.